So in today's video, we'll talk about hash table. We'll look at the inner workings of a hash table. Before we go into the inner workings of a hash table, first let's take a look at when to use a hash table. So suppose you want to look up an item quickly by a key. That's one place you'll use a hash table. So there's another option also if you want to look up quickly by a key, which is called a binary search tree. And I have a video on binary search tree. You can find it in my videos. So a binary search tree gives you additional benefits like if a key is not present, find me the object with the closest key, or find me the object with the minimum key, find me the object with the maximum key, or sort all the keys by order. So these are additional benefits you get in a binary search tree which you do not get in hash table. So then why would you use a hash table ever if binary search tree gives you all these extra features? And the answer is speed. So hash table lookup is way faster than a binary search tree. In big O terms, binary search tree, a lookup is big O of log n. But in hash table, it's constant time. It's big O of 1. So in simple terms, lookup is much faster in hash table. So if you have a requirement where all you care is I'll give you the key, you give me the object that corresponds to the key, a fast lookup, then you'll use a hash table. So now, before we go into the inner workings of the hash table, there is a few other things we need to get into. So one of those things is the hash code. So what is a hash code? So hash code is nothing but just an integer for an object. So I give you an object, you give me an integer, and that integer has to be as unique as possible. So as unique as possible is important because it doesn't have to be unique. Ideally, it should be unique, but it doesn't have to be. Even if it's not unique, it will work. And we'll look into it more later. So let's see an example of a hash code. Okay, so suppose I want to look up states by their abbreviation. So my key would be the abbreviation of the state, and the value would be an object that contains the details on the state. So say key will be California, CA, key would be MA for Massachusetts, key would be NY for New York. So we have a requirement where we are given a key which is the abbreviation of a state, and we want to look up the details on that state very fast. So before we do that, we need to find a hash code, and which is an integer value for every key. So one way to do this is, suppose I assign a number for every letter. Say A is 1, B is 2, C is 3, M is 13 for Massachusetts, and then whatever, and then Z is 26. So for California, if I want a unique number, I can do something like this: 26 into C plus A. 26 because there's altogether 26 possibilities. So for letters, there's 26 letters altogether. So if we do it this way, we can convert every abbreviation into a unique number. So if I do 26 times C plus A, which will be 26 times 3 plus 1, which is 79. So I can convert California, CA, into a number 79. And Massachusetts, let's look at Massachusetts. So Massachusetts would be 26 times M plus A, which is 26 times 13 plus 1, which comes out to 339. So Massachusetts, 339. So basically, this is all what a hash code is. You just take that key and convert it into a unique number. Now that we have a hash code for every key, let's see how to create a rudimentary hash table. So suppose now that I know that I can take the abbreviation for any state and convert it into a number, let's see how I can create a hash table out of it. So what if I create an array, okay, that can take all possible abbreviations, which is like 26 times 26, which is 676. Okay, so suppose I have an array of size 677, which goes from 0 to 676. Okay, and now what I do, for every state I just put it into that array index. So for California, we saw it was 79, right? I will just go to index 79 and store California in there. And say Massachusetts was 339, right? So I'll go to index, so this is 79. I will go to index 339 and store Massachusetts in there. So this will work, right? Now if I want to find California, all I need to do is find the hash code of CA 79 and go to that index and get it. Same for Massachusetts and same for any other state. So this does give us a fast lookup. In array, a lookup is by index is supposed to be constant time, big O of 1. So this gives us a fast lookup. But the problem here is, if you see all together, I have 26 states to store, and sorry, not 26. We have I think 50 states in US. So we have 50 states to store, but instead of 50, an array of size 50, I have an array of size 676. The whole of the rest is wasted. So how do we fix this? Okay, how do we avoid this wastage? Instead of 50 states, why am I, for a size of 50, why do I need such a big size? So the way it's done in hash table is we don't take all possible values of the hash code. Instead, what we do is we take an array of size double the number of keys. So I have 26, not 26 actually, total number of keys is 50, right? So instead of for 50 states, I will take an array of size 100. So maybe just say 101, 0 to 101. Actually 0 to 99 would be good, yeah. So array of size 100. You just take the double the number of keys. So total keys I have, total number of keys I have is 50. And if I have 50 keys, I will just take an array of size 99. Now you might think, how will this work? Because California is 79 and Massachusetts is 339, which is beyond this. So California will fit here, Massachusetts will not fit here. So how do you bring it down to 99? So that is where a compression function comes in. So the way compression function is defined is so what we do is H is the hash code. So A into hash code plus B mod P mod N. So A and B are just two large numbers, any large number. So for this example, let's just say we take 10. So 10 into H plus 15. Again, in a real example, no real world, you'll take much bigger numbers. But just for this example, we'll take like this. A into hash code. So for California, this will be 79. For Massachusetts, that was 339. California, 79, yeah. So A into hash code plus B, which is here, mod P is just some arbitrarily large prime number. For the sake of this example, we'll say 13. Okay? And this whole thing, mod the total number of buckets. So here we have total number of buckets as 100. So mod 100. So since I'm doing mod 100, no matter what this comes, if you do mod 100, that value will be between 0 and 99. So that's how we convert from the hash code to the bucket number. So this is a bucket number. You can these are all buckets. So A into hash code plus B mod some large prime mod the total number of buckets. But now you might think, if I do it this way, is it not possible two items might end up in the same array index? And you'll be right, it is possible. So that's why what we do here is we don't put just the object. This itself is a linked list of objects. So the compression function I told you, where you take a hash code, compress it to a number, and within that number it's a linked list. So you'll have an item like this which points, so basically this is how a linked list works, right? You'll have, so these are all individual states. So what you do, you take the hash code, you compress it to a number, say that number comes out to 34, and then within that number you have a linked list of state objects. So there will be California, or there might be something else, there might be something else. So what you do, if you have to look up or to add, you first, say suppose you're adding, you find the hash code, compress it, you find the number, and then you add that item. Then again another item comes, you take the hash code, do the compression function, suppose a collision happens, you'll add it as the next item in the linked list, and so on and so forth. And when you want to look up, it's again the same thing. Suppose you have all the items stored in this array. Now I will say, give me Massachusetts. So what you will do, you will first take Massachusetts, take the hash code, find the compression, you'll come to the index. Then once you come to the index, you go through every single item in the linked list and you do an equals. So this is why anytime you have to store an item in a map, okay, where the key is the object, that key object should override both hash code and equals, because hash code is only going to get you till this bucket, and once you get to the bucket, to find the item you need equals. So this is why anytime you store anything in a map, say a Java map or something, the key, whatever key you use, should override hash code and equals, both. So this is important. The key should override both hash code and equals. If the key is an object, if it's an integer, it's already taken care of. But if you're using some custom object to store as the key, it should override both hash code and equals. So this is pretty much how a hash table works. So we went through compression function, we went through total number of buckets. Again, total number of buckets is basically, it's just the number of keys you're storing. And as you keep adding keys, at some point your bucket, so once the total number of buckets is 1.25 times the number of keys. Okay, so suppose you first add a key, then your keys keep increasing, and at some point your keys increase to a point where the total number of buckets is not double the key, but it's only 1.25 times the number of keys. Suppose you reach that point. At that point, what you do is you resize the array. You make the array double size and copy all the items over. Now that time, one thing to remember is you cannot directly copy, because if your array size becomes double, your n changes. So the bucket number, there is a factor n, right? A into h plus b mod p mod n. So rest everything will remain the same, but n will change. If you make so from 100, if I do 200, this will change. So you cannot directly copy 0 to 0. You'll again have to do compression function on all the keys and copy them over to the new array. So this is the point. So first, total number of buckets is twice the number of keys, and you keep adding keys. At some point, total number of buckets is only 1.25 the number of keys. That's the point. You double the array again. So we covered that part. We covered the part of importance of overriding hash code and equals, and yeah, big O. So in big O terms, if you have a good enough hash code where it's as unique as possible, and like I said, your number of buckets is at least 1.25 times the number of keys, ideally 2 times, but at least 1.25 the number of keys, Given those two conditions, that your hash code is good and your total number of buckets is good, the insert, search and delete all on a hash code is constant, big O of 1. So the average runtime for insert, delete and lookup for a hash table is big O of 1. The worst case can be big O of n. So I'll tell you how it can be big O of n. Suppose I have a very bad hash code where all my states end up in the same bucket. Then what will happen? I will find the bucket quickly, right, from the hash code, but then I have to go through every single item in that linked list to find it. So which will make it big O of the number of items. So badly designed hash table will have big O of n as the lookup time. And badly designed means either your hash code is not good or your number of buckets is very less. So that's all. I think there is nothing more I need to cover for hash table. Thank you.